Hello students, I will be covering your class 10th mathematics, and the very first chapter from which we are going to start is real numbers. Now I have divided this real number in a number of topics. First of all, I will revise the number system which you have studied in class 9th. Then I will be taking up the Euclid's division lemma, although you are aware of what this division lemma is, and we use this division algorithm, but now you will know what it is. Third, we'll be covering fundamental theory of arithmetic. Then, although you are aware of irrational numbers, now we'll cover some more relations related to it. Then we'll be covering up the rational numbers and the decimal expansion. First of all, let us revise the number system which you have studied in class 9th, just to brush up your basics. As you can see, this is a number line. It extends from minus infinity till infinity, and each and every point on this number line, whether it is an integer or any point in between integers, it is represented by a unique point, a unique real number. And the converse is also true, that every real number is represented by a unique point, as well as every point is represented by a unique real number. Now, this was the definition which you have studied in class 9th. What is a rational number? A rational number is a number which can be represented in the form of p by q, where q is not equal to 0. Now, if you want to find a rational number between two numbers, what we'll do, we'll simply add them and divide them by 2. That will give the middle point between those two rational numbers, that is between x and y. Now let us try a problem. You have to find 4 rational numbers between 2 and 3. It's very simple. Add 2 plus 3 and divide it by 2. That will give us 2.5, or rather I say 5 by 2. Then we'll add 2 plus 5 by 2, and then we get 9 by 4. If we add 5 by 2 plus 3, we'll get 11 by 4. Now we also want the fourth number in between them. So what we'll do, we'll add 2 plus 9 by 4, which will give us 17 by 8. Now we want to categorize rational numbers. So if we take a decimal expansion of a rational number, it will either be terminating or non-terminating recurring. What does that mean? So how will it be terminating? If we take 1 by 8, it will be terminating, that is, we'll have 0.125, and after 5 it has terminated. We have got a 0 in our remainder, so that's why it is terminating. And if we take an example of 1 by 3, that will be non-terminating recurring. It will keep on repeating itself again and again, as we can see 0.333, and it will just go on till infinity. Same is the case with 1 by 7 also. After we get 0.142857, it will keep on repeating itself. So 1 by 3 and 1 by 7 both are non-terminating recurring. So a decimal expansion of a rational number is either terminating or non-terminating, and converse is also true, that is, a number whose decimal expansion is terminating or non-terminating recurring is a rational number. Now let us try a problem. As we can see, 1.7272, and it will keep on repeating itself. This is a non-terminating recurring. We know it's a rational number, but we want to represent it in a form p by q, as we have defined rational number. As we know the definition of rational number, that is, it can be represented in the form of p by q. Let us suppose this number is x. So if we multiply left side by 100, we'll multiply the right side also by 100, and we'll get 172 point the same non-terminating recurring digits, that is 727272. Then we subtract x from 100x, and we'll get 171, and the non-terminating recurring digits will be subtracted by itself when x will subtract from 100x, and we are left with 171 is equal to 99x. And now we can easily say that x is equal to 171 by 99, which is equal to 19 by 11. So as we have represented this non-terminating recurring decimal expansion in the form of p by q, so we can say it is a rational number. Now a number say s is called irrational if it is not represented in the form of p by q, where q is not equal to 0. Examples for this will be pi, which we know is 3.141592. Although we use pi is equal to 22 by 7, but that is just for the sake of proximity. It is not the actual value. 22 by 7 is not the actual value of pi. It is just the proximity which we take. The actual value of pi is 3.141592, and it will keep on going. It is a never ending decimal. It will not terminate. Same is the case with under root 2 also. Under root 2 is equal to 1.412156, and it will just keep on expanding. It will never end. It will never terminate. As I said just now, the decimal expansion of an irrational number is non-terminating, non-recurring. As we have seen the examples of pi, under root 2, even under root 3 also. These are non-terminating and non-recurring. That's why they are known as irrational numbers. And converse is also true. If we have a decimal expansion which is non-terminating and non-recurring, it will be known as an irrational number. Now let us try a problem. Find an irrational number between 1 by 11 and 2 by 11. It's very simple. As we know, it cannot be represented in the form of a fraction. So first of all, we'll take the decimal equivalent of 1 by 11. The decimal expansion of 1 by 11 is 0.0909, and it will keep on repeating 0909. So if we want an irrational number between 0.09 and between 2 by 11, which is equal to 0.1818, we can write any decimal number in between these two, which is non-recurring as well as non-terminating. It will keep on expanding. We can write any decimal number which is non-recurring and non-terminating in between these two. As this is the decimal expansion of 1 by 11 and 2 by 11, we have to write an irrational number between these two, and it has to be in the form of decimal expansion because irrational number cannot be represented in fraction. So that's why we have taken the decimal expansion of 1 by 11 and 2 by 11, and we write a non-terminating and non-recurring number in between these two decimal expansions. And there are infinitely many solutions for those. One example is 0.109100910009, and it will keep on expanding. It will not repeat itself. Now we look at identities which are related to square root. First of all, square root of a multiplied by square root of b is equal to square root of a into b. Square root of a divided by b is equal to square root of a divided by square root of b. We know this formula. This is a plus b into a minus b is equal to a square minus b square. For the square roots, the formula is square root of a plus square root of b into square root of a minus square root of b is equal to a minus b. A plus square root of b into a minus square root of b is equal to a square minus b. The same formula, that is a plus b into a minus b is equal to a square minus b square. Square root of a plus square root of b into square root of c plus square root of d is equal to square root of a into c plus square root of a into d plus square root of b into c plus square root of b into d. Square root of a plus square root of b whole square is equal to a plus 2 into square root of a into b plus b. You are aware of this formula also. A plus b whole square is equal to a square plus 2ab plus b square. Now let us do some examples related to these identities. Square root of 11 minus square root of 5 multiplied by square root of 5 plus square root of 11. As we can see, this is related to the identity a minus b into a plus b is equal to a square minus b square. So it will be under root of 11 square minus under root of 5 square, which is equal to 11 minus 5. We get 6. Let us take another example. 5 minus square root of 5 whole square. Now we know a minus b whole square, which is equal to a square minus 2ab plus b square. This will be equal to 25 minus 10 under root 5 plus 5 and equal to 30 minus 10 under root 5. We have seen identities related to square root. Now we'll see laws of exponents. A raised to power m into a raised to power n. As the bases are same, this will be equal to a raised to power m plus n. A raised to power m whole raised to power n is equal to a raised to power m into n. As a raised to power n is dividing a raised to power m, it will be subtracted from m. So a raised to power m divided by a raised to power n is equal to a raised to power m minus n. Here m has to be greater than n. A raised to power m into b raised to power m. This can also be written as a into b whole raised to power m. Nth root of a is equal to a raised to power 1 by n. A raised to power m divided by n is equal to nth root of a whole raised to power m. Now we'll cover the second topic, that is Euclid's division lemma. First of all, we should know what lemma means. Lemma is a proven statement which is used for proving other statements. So the theorem is, given positive integers a and b, there exist unique integers q and r satisfying a is equal to bq plus r, where r is greater than or equal to 0 and less than b. This technique is used to calculate highest common factor, and this is Euclid's division lemma, although you have used this technique for dividing many times. For those who are not aware of what HCF is, highest common factor, let me tell you, HCF of two positive integers a and b is the largest positive integer q that divides both a and b. Now that we know HCF is calculated by Euclid's division lemma, let us see the algorithm which is used to calculate HCF. Now let us suppose we want to find HCF between C and D. So we'll divide D by C as D is smaller than C, and we'll obtain Q and R, that is quotient and remainder. When we divide C and D, we get Q as quotient and R as remainder. If R is equal to 0, then D is the HCF of C, and if not, if R is not equal to 0, then we'll again apply the division lemma between D and R. So this time we'll have, say, D is equal to R into some quotient plus remainder, and we'll check if remainder is equal to 0, then R is the HCF of C and D. We'll continue this process till our remainder is 0, and the divisor at whatever stage we get a remainder 0 will be the required HCF of C and D. So now we'll cover our third topic, that is fundamental theorem of arithmetic. Now as we know, every composite number can be expressed as a product of prime numbers. So this theorem says every composite number can be factorized as a product of prime numbers, and this factorization is unique apart from the order in which they occur. That is, the order may not matter. If we are multiplying 2 into 3 or 3 into 2, it will not matter, but the factors of prime numbers which are multiplied to get that composite number will be unique. Now let us take an example. 2 raised to power 3 into 3 into 7 raised to power 3. This gives us 8232. So 8232 is our composite number, and this is factorized by the prime numbers, which is a unique factorization. And mind you, the order will not matter. If we are multiplying 3 before 2 or after 7, it will not matter. So the order is immaterial.